Hello. Um, in the previous lecture, in the previous lectures, we looked at the public health data. We did regression, regularized regression, lasso, bridge. And in this lecture, I want to do go over a simulation example that illustrates the um, difference between ElasticNet and lasso. Both of them do variable selection. Um, but there's a slight difference, and the difference is when the predictors are correlated. When there's a strong correlation between predictors, lasso tends to, and if they are associated with the response, lasso tends to uh, pick only one of those highly correlated features. And the one that is picked is more or less arbitrary. That's a problem because if you have a couple of highly correlated predictors, um, how is it that one of them is associated with the response but the rest not? So in order to fix that problem, people came up with ElasticNet, and they were able to show that ElasticNet is something between Ridge and Lasso. It has the variable selection property of Lasso, but in addition to that, if you're dealing with a situation where a group of highly correlated variables features are associated with the response, um, in contrast to lasso, which only picks one of them, ElasticNet has this grouping effect and is able to, and essentially captures all of them, which is more reasonable. Again, if you have a group of variables that are highly correlated, um, if one of them is selected, is added to the model, it makes sense that the rest of them also should be added. That's the big difference between lasso and ElasticNet. That's the take-home message, and this lecture is about illustrating this and just going into details using a simulation study. I also will go over the original ElasticNet paper, um, and we will identify the sections of the paper which specifically refer to this major point that we want to discuss. Okay. Sorry, this is a different. I'm running a couple of things at the same time, so this is totally irrelevant too. All right. Okay, so first we want to generate data. Any simulation study is about generating synthetic data. Oh, another thing that we also do in this lecture is we show how to um, use Bootstrap to quantify the uncertainty of the estimates. Okay, so we're doing two things. Um, we show the difference between ElasticNet and Lasso, and we use Bootstrap to quantify the uncertainty, the error bars, and then how to plot that. So we do more than two things, but these are the major things. So the data we're generating, the sample size is 200. We have 50 features, and out of those 50 features, 10 of them are relevant. 10 of them are associated with the response. The design matrix, the feature matrix, is a random matrix. So we just generate a random matrix, fill the elements of it with a Gaussian standard Gaussian distribution, zero mean unit variance, p columns and rows. This is the standard deviation of the irreducible error, and this is the irreducible error. This is the true beta, we call it beta star, and it's a vector filled with zeros where we pick the first k elements and say the first k elements are 1. Okay, this is the specifications of the data generating process. Okay. So now if here we have this routine, so far, I mean, as you can see here, the elements of this matrix, of the design matrix, are independent. They're identically distributed, and they all come from a Gaussian distribution. Zero mean, unit variance, no dependence. But we said at the beginning of the lecture that we want to study how dependence changes the estimates. So here we have this routine, which we're saying essentially if it's true, then go over the first k features. Remember, the first k features are the ones that are relevant, that are associated with this. Go over them and change them. And the way we change them is we say all of them are um, are 99% the first feature plus 1 minus 99%, which is 1%, some random noise. So essentially, the correlation between what we're doing here is we make the correlation between the first k features to be q, whatever q is, and q is 0.99. Okay, so let's just run this. Okay, so let's look at x. Say c is the covariance of x, and um, you see the first 0.87, 0.87, 0.87, 0.86, 0.87, 0.87, 0.87, and then suddenly after the 10th one, it drops to 0.03, 0.06. So these correlations, these covariances, are significantly less than the first 10. The first 10 features are highly correlated, and then the rest are not. And these small numbers, 0.03, 0.06, 0.07, 0.05, they indicate that, for example, the 6th feature and the 12th features are not correlated, almost not correlated. The 6th feature and the 13th feature are not correlated, whereas the 6th feature and the 9th feature are highly correlated, 6th and 10th highly, 6th and 11th. So after the 10th, they are not. You see 1 and 9, 1 and 10 are highly correlated. Now if we do this false, then we see that 1 and 2 are not, 1 and 3 are not, so they are just almost independent. These small numbers um, tell us that the pairwise covariance is significantly small and therefore they're almost independent. Okay, so here we have the option to generate data from an example where the first k features are dependent or not dependent. Now what is this line doing? It's just a old equation, x beta plus noise is y, so we make a noisy observation and then we set the train and test splits 80%, 20%. Okay, and this is similar to something that you may see in the project you're asked to do. Okay, so we're splitting, you're saying that we, this essentially indicates that in the future, a few lines down, we're interested in splitting the data into two portions, 80% train, the rest test. We can change the 80% to whatever we want, but here's 80%. How many times do you want to do this? 100 times. And for each of those 100 times, we like to calculate the R square. The R square for the test, the R square for the train, and both for elastic net and lasso. So here we're just initializing these um, arrays that we're going to fill in each iteration. So what are we going to do in each of these m iterations? That's what's going to happen in the for loop. The first line of the for loop creates a shuffled, um, essentially we have these numbers 1, 2, 3, 4, 5 to n, and we shuffle them to create a random order. Cross validation, the first step is always shuffling, as you can see in this figure. 1, 2, 3 to n is they are shuffled. Um, for leave one out cross validation, we don't shuffle it because it doesn't matter. At each moment, we just take one data and we're going over all the data points, so that shuffle or not to shuffle, it wouldn't make a difference. Anyway, the first um, n-train samples um, tell us the index of the training data, and the rest tell us the index of the test data. So we have these shuffled indexes, and we look at the 1 plus n train to the nth one to get the test portion. And then we create the x train, y train. Excuse me. So we take the rows indexed by the data points in the training set to create X train, and then we do the same thing for Y train, X test, Y test. In this part, we fit elastic net, calculate and record the train and test R squares. Elastic net refers to any alpha that's between 0 and 1. And the reason I pick 0.5 is pretty arbitrary. I could have picked 0.4, 0.3, and in fact, people also it's an option that we have to also cross-validate over the values of A in addition to the values of lambda. And sometimes it may make a huge mistake, but our working assumption is that it won't make a big difference, and we pick something in the middle being 0.5. Okay, we call the cross-validation function of the GLMnet library. We provide it with the training data. We tell that there is no intercept. Don't fit an intercept. Why are we not fitting an intercept in this example? Why should this be false in this specific example? The answer is here. The data generating process. Do you see an intercept? No. If I had an intercept here, let's say something like this, plus a0, uh, a0 could have been anything, 2, 1, whatever, then I would have also fit this, call this function with without making the intercept flag or option 0. But since we are not having it, then um, we just say this is false, so don't fit an intercept. Typically with real data, we all we, we have an intercept, so it rarely happens that we do this false, but this is a simulation study. Our focus is something different, so we make this false. Alpha number of faults. Take the using the CV fit object, we find the lambda that minimizes the cross-validation error, feed it to the glmnet function, get a fit, use that fit to predict the response for the X train and the X test. So the predict is a function in R that you can feed it, you can feed to predict a fit object and a training data and receive in return a prediction, obviously, right? And in this specific case, because the model is linear, this is essentially just equal to saying take X train multiplied with the fit, the beta coefficients, the estimated beta coefficients. So this is X beta hat, essentially. X train beta hat. And if you have an intercept, also add the intercept. So I just added here because this is the general formula. So calling this line or this line will give you the exactly same result. And the same thing for the test. The only thing for the test is that um, we use the test features together with the estimated coefficients to get an estimate for the response. That's all. Once we have our estimated responses for the test and train, by comparing it to the actual test and train data, we can find the R squares, which is supposed to be a number, which is a number between 0 and 1. And the reason we use the R square is to have a measure that is unitless. We could have used mean squared error. These two are proportional, but R square is a normalized version of the mean squared error. It allows, it lends itself well to comparison across different models or different data sets with different scales, units. Okay, so that's the main reason. So is there an error in this line? What is the problem with this line? What is the problem with this line? The problem is that here we are using, I mean, it's not a big problem, but R square is not this. Use Y test. This is the formula for the R square for the test. So you can see you can just get rid of these two. We have the actual Y minus the Y hats, and then you have the yi minus the means summed. So this can be a sum or a mean, and that's what we're doing here. So I could just replace this with sum, and the result will be the same. Not that sum is equal to mean, but the division of two sums is this equal to the division of the means. Okay. Now then we repeat the same couple of lines here, but we do them for lasso. And in order to do them for lasso, we have to set the alpha to 1. We get our fit, we make our predictions, then we calculate the R squares, and we have to fix this. Okay, and then here we print the iteration number and the quantities we're interested in each iteration, the R squared test for lasso, elastic net, the R squared train, lasso, elastic net. The R squares are pretty high, 0.99. Now let's increase the irreducible error so that we see a bigger difference between the train and test performance. The data we're generating is too clean. Okay, so we're starting to see some differences. But let's increase it a little bit more. Okay, this is much better. This is like a bit more. The R square is still pretty big. In real data, we rarely see an R square of 0.95. I mean, I don't want to say rarely, but okay, so you see the test R squares, not always, but tend to be smaller than the train R squares as we expect it to be. And What is the CV fit? This is the last lasso fit, okay? And the minimum selects around 17 predictors. Remember, this is a synthetic data, so we know what is the true number of um, relevant features, and we know it's 10. So it's not bad because Lasso is picking something close to 10, but this just shows that whatever estimate we get, there's always some error, obviously. And here, because we know the data generating process and the truth, we can clearly say, okay, um, Lasso is selecting more variables than are actually associated. But that's okay. All right, let's look at the box plots. So the panel, so this is not a great figure, and for the project you need to spend some time and create a nice figure where the box plots are side by side, they have different colors, the labels are clear, and I'm not going to do this. This is going to be your work, so don't take this, but just what we want to see here is just plot them just to get a sense. So this is the R square for the test. This is 85, so the median is around 0.87. This one is slightly, which is a train, it's slightly higher. So let's repeat this with a little bit higher noise. So again, two interesting things. Not very. They're almost trivial. The test R square is slightly smaller than the train R square, but the test and the train R square are not too far from each other, which shows that cross-validation is doing a pretty good job. If the train and if there was a big discrepancy between the train and the test error, um, that would be an indication that, um, for example, there is probably overfitting going on. But because these two are not, I mean, sometimes they are, but mostly they're not too far from each other, then this is all just qualitatively speaking, obviously. Now the next thing is we want to use bootstrapping to create bootstrapped data sets from the original data and use the variability of the estimates based on those bootstrap data sets to calculate error bars. to quantify uncertainty. So each bootstrap um, sample gives us one bootstrap estimated set of coefficients, and we need to store them. So we are here we're creating a matrix with p rows. So each column is going to be one estimate, and then we have p rows, and then we have bootstrap samples number of columns, which each of them will be corresponding to one of the bootstrap samples. We have a for loop where we're repeating there. We are sampling with replacement. That's bootstrap. How do we create a bootstrap data set? These are our observations. This is the original data. Each bootstrap dataset contains n observations sampled with replacement from the original dataset. Each bootstrap dataset is used to estimate an estimate of, for us, is beta. We do this to estimate beta. So here, this is just sampling with replacement. Sampling in the numbers between 1 and n with replacement to get the indexes, the pointers to the data points, use those pointers to the data points to create a bootstrap um, feature matrix and a bootstrap response. So for each bootstrap's data, we fit elastic net. Meaning we do cross-validation on it, get the lambda, fit um, fit it again, and take the estimated set of coefficients and store it in the empt column of beta en bootstrap. Repeat the same thing for lasso. And here we're just printing what sample, so you have a sense of how how fast this is all moving forward. Once we're done with going through all the iteration of bootstrapping, we use that all those estimates to calculate the standard errors. Alternatively, you could also use quantize to find upper and lower bounds. Okay, so this is what we're doing here. In that line of code, we compute the standard errors of these bootstrap estimates. And this is a formula. Essentially, we're looking at the variability of this variable. We don't care about the median, we don't care about the mode, where it's happening, or the mean. We just care about the width of this. Okay, so these are bars. Then we fit elastic net to the whole data. Fit lasso to the whole data. Create a data frame where we store the feature, which is an index of the feature. In the real data analysis, this will be a column of the names of the actual names of what the features predictors are. Then we have the values, and then we have the bootstrap errors, which we take to be two standard deviations. So beta feature 1, the estimate is 0.77, the bootstrap standard deviation or error bar essentially is 0.79. So you see the estimate is pretty good because yes, the 10th one, which is supposed to be non-zero, is 0, but the first 9 features are non-zero. The bootstrap standard error tends to be tend to be very large. But we don't, you see the labels here? They're pretty meaningless, so we need to rename them. Feature value error. We repeat the same thing for lasso. Sorry, elastic net. And then we just plot the um, plot the coefficients. So disregard these are the error bars that we found using Bootstrap. They're pretty high, and that's not surprising because we added quite some noise. But in high dimensions, Bootstrap tends to be less reliable. And what we mean by high dimensions is scenarios where N and P close are close to each other. But when the sample size is significantly larger than the number of features, then these error bars are more reliable. But let's disregard the error bars for a second. We have two panels, and the right thing to do would be, which is something that you guys need to do, is to appropriately label these figures, not the way I'm doing it, and you're going to do this. But from the code, um, the question I have is, right, the first panel, second panel, which one is referring to lasso or elastic net? And well, the code tells us, but just by looking at this, we know that the first 10 features are associated with the response. We also know that the first 10 features are highly correlated. We also know that in such cases, lasso tends to pick one or a few of them, not all, and will suppress the rest. Whereas elastic net is able to um, have this grouping effect where if a group of variables are correlated, they are either all in or all out. You see the first 10, well, the 10th one is 0, but you see this bulk, they're all more or less in, whereas for lasso, only these few are in. Lasso has only picked these 3, whereas ElasticNet has picked all these 9, the first 9. Now what happened here? When lasso is not picking the rest correlated one, the estimated coefficient for the few that are picked, for this one for example, is larger. Okay, so this paper was published in 2005 in the Journal of the Royal Statistical Society B, introduced ElasticNet. It's pretty technical, and I don't want to if you're interested, yes, you should read it. But um, I want to draw your attention to the abstract um, to again emphasize a few points that I've been repeating throughout this lecture. But here I want to use the original text to refer to it. Okay, so what is the abstract saying? Well, one claim is that real-world data and simulation studies show that elastic net often outperforms the lasso while enjoying a similar sparsity of representation. Okay, so sparsity of representation here means that it picks um, a few predictors that are associated with the response and then clamps the rest to zero. Okay, but there's nothing new here. The major thing is that ElasticNet encourages a grouping effect where strongly correlated predictors tend to be in or out of the model together. This is something we saw, and this is why we like ElasticNet, why we prefer ElasticNet to Lasso, because in real uh, life, in real data problems, predictors typically are correlated. And again, it doesn't make sense if there are, if a group of predictors are correlated, um, especially if they're highly correlated. It doesn't make sense for one or two of them to be in while the rest are clamped to zero. They should be either all in or all out, unless you have a good reason to distinguish between them. But statistically speaking, the only thing we see is the correlation, so we don't have a good reason. Okay. But this was essentially the main sentence I wanted to focus was this. Okay. So one thing we like to do to improve this application here is to order the features from the most important or the strongest to the least important. And um, we have to say which model is a reference model. So we need to change the order of the factor levels by specifying the order explicitly. And what we are doing is that we use the lasso. Yeah, let's not use lasso. Let's use elastic net. So I want to use. I want to um, sort the estimated elastic net coefficients in a decreasing order, and that gives me a sequence of indexes to the coefficients, and then I use that to plot the coefficients of lasso, so it makes the two plots comparable. Nine, nine. 1, 1, 8, 8. So it's the same order, and the order is determined by the magnitude of the estimated coefficient for elastic net. The order determined by the magnitude of the estimated coefficient of elastic net determines the order with which we plot the estimated coefficients of lasso. Okay. Now let's repeat the same experiment and with the difference that we are creating independent features. So let's just reduce this. Let's just go to true. So we want to run the whole thing with smaller noise. Okay, so this is elastic net takes all 10. Lasso sets sum of the first 10 to 0. Now I'm just making the dimensions a little bit smaller. again, the same thing. The grouping effect we see here, we don't see for lasso. Now, something I want to do is I want to make this 50 and I make this 50 and I want to reduce. Since we don't care much about this at the moment, for the next run I will make this smaller. Okay, now let's run this once more but with a larger noise. So as we can see, the bootstrap error bars are pretty big here, and in some sense they are too big. They are unreliably big, and Now we're looking at a case where the number of relevant features is much smaller number. It's 4, very few, and we want to see how the results are different and if that whether that gives us some insight into what is going on. Let's increase the sample size. Okay, so as you see, I'm just running the code over and over again for different combinations of sample size, feature size, noise error, and what we can see is when the sample size is large or when the noise variance, the irreducible error is the, the standard deviation of it is small, the difference between elastic net and lasso is also small because there's so much signal, there's so much information that more or less, regardless of what you do, um, you're able to pick up the relevant features. But as we reduce the sample size, or increase the noise variance, the difference between elastic net and lasso becomes uh, much clearer. And as we said, lasso is clamping these coefficients to zero, whereas elastic net is picking them up. Now let's just run the whole thing with the dependent variables to be false. And the difference we expect to see is that these coefficients, which are clamped to zero, now will not be zero anymore, because they're now the predictors are independent, and when they're independent, then lasso is uh, able to deal with them all together. It allows them to be, it allows the relevant features to be estimated. Whereas when they are correlated, it will clamp some of them to zero. Well, let's see if that happens. Yes. See? Now lasso and elastic net are not very different anymore. Okay. So I think we were able to get across the major points, take-home messages. There's something I want to take a look at here, and well, let's run this one last time, and let's just increase everything here. The offshore is too small. Actually, just so that we save some time. Two times. Let's do this two times. And the reason is that I'm not. We don't care anymore about the bootstrap samples. I want only to look at the this part of the code where we fit the data to the whole data. plotting, but let's go here. Okay, finally. Hmm. Oh, okay, now it is. You see, in this case, they're not very different. It's because dependent variables is false. Let's make this true. I'll run this for the last time. Okay. I don't know what's going on with the figures, but let's just clear the plots. I think because we have too many, not too many, but because we have a couple of hundred of predictors, take some time to plot them. But what I want to draw your attention is that ElasticNet, remember the true coefficient values is 1, and ElasticNet estimates them all around 1, whereas Lasso, when they are dependent, um, overestimates some of them and then underestimates the rest. Okay, so I think this is pretty clear. We had a reasonable R example, and we went into deeply into ElasticNet, um, lasso, cross validation, the tuning of the parameters, and bootstrapped error bars, and we also learned that bootstrapped error bars in these data regimes can be um, unreliably large. Okay, so I think this is it for this lecture, and see you next time. Thank you. Bye bye.